Welcome to qnawire.
Okay, we need to figure out how many moles of air are in the lungs of an average person with a total lung capacity or volume of 3.8 liters. We're also told that the pressure in that person's lung is 1.0 atmospheres. And we're told that the temperature in those lungs is 37 degrees C. And we're asked how many moles of air. So let's use N for moles. And that's what we want to know. Well, does this look familiar to anyone? We've got volume, pressure, temperature, moles. How do we relate all of these things? The ideal gas equation, right? PV equals NRT. I mean, the only thing we're missing is R, and R is just a constant, right? R is a number that relates all of these other numbers, right? We've got variables, P, V, N, and T. Those can change, but R never changes. So we can just get R from our textbook, right? It's always fine to just look up R and use it, so long as the units match. So, we want R, and we want it to be in units of liters. That would make things useful. Maybe atmospheres. We've got one little issue here, right? They told us the temperature in degrees Celsius, but whenever we're dealing with the ideal gas equation, we like to use Kelvin, right? And how do we change Celsius to Kelvin? We add 273.15. So 37 degrees Celsius is equal to 273.15 plus 37 Kelvin. All right, so altogether, I'm going to have my calculator, 273.15 plus 37. I get 310.5, but let's just call it 310. 310 degrees Kelvin. Okay, so now if we can find R in units of Kelvin, atmospheres, and liters in our textbook, what do I got here? Or, you can Google gas constant, go to Wikipedia, and they've got a table of all the different values of R and in various units, right? So we said we want it for liters, atmospheres, Kelvin, and moles. And wouldn't you know, on Wikipedia, they say that R is equal to 0.08206 liters times atmospheres divided by Kelvin divided by mole. And that's exactly the units we were looking for. So I think we can really just take this equation, PV equals nRT, rearrange it to solve for n, because that's what we want to know, plug in all of our values, and we should be good to go, right? So what would this look like if we solved it for n? We can divide both sides of the equation by RT, right? That's fair. That's just doing algebra. Divide this side by RT. As long as we divide this side by RT, that's totally valid. And the RTs on the right-hand side will cancel out. And this will imply that N is equal to PV over RT. And now we know we can plug in our 1 atmosphere. Okay, P was 1 atmosphere. Our volume was 3.8 liters. R, we said, was 0.08206. And that was liters times atmospheres over Kelvin times moles. And we know the temperature was 310 Kelvin. Okay. And let's make sure the units check out. Atmospheres here cancels with atmospheres here. Liters here cancels liters there. Kelvin in the denominator of the denominator cancels with Kelvin in the denominator itself, right? And let's double check, right? We had liters in the numerator, and then we had liters in the numerator of the denominator. So those do cancel. And we had atmospheres in the numerator, and we had atmosphere in the numerator of the denominator. So those do cancel. Totally fine. Okay. So our final unit is going to be moles, and it's in the denominator of the denominator, which is equivalent to being in the numerator. So whatever answer we get is going to have the units of moles, and we just need to plug the numbers in right now. So, right, we got 1 times 3.8 divided by, there's two ways we can do this. We can say divided by 0. In a calculator, you can do it one of two ways. You can say 1 times 3.8 divided by 0.08206, and then also divided by, so you do another division symbol, you say 310, or you can say 1 times 3.8 times, and then put in parentheses 0.08206 times 310. Either way will get you the same answer, so long as you enter everything correctly. No matter what, you get 0.1493. So, okay, so 0.1. How many significant figures do we have? It looks like we have two significant figures. So I see 0.149. That's going to round up to 0.15 moles. So there's 0.15 moles of air in the lungs of an average person.